This chapter is about a recurrent neural network. Before we study RNN, let's turn our attention to sequential data first. We have learned many machine learning methods, and we use data to train them. But the data we used so far is assumed to be IID. So what is IID? IID means independent and identical distributions. So basically that means each data we use is independent to each other and they are from identical distributions. So that is the underlying assumptions of data we use in machine learning algorithm. But there are some other data which doesn't actually satisfy those assumptions, and the sequential data is one of them. So let's take a look at this example here. So these are the example of sequential data, like frame from video and words in sentence, etc. So for example, you have a sentence like, I go to school. Then the word school actually depends on I go to. Okay, each word is not independent anymore. These are dependent words. The word school depends on I go to. And also the word to depends on I go, etc. So in sequential data, the data is not independent anymore. They are dependent. Okay. So that's one of the characteristics of sequential data. So that's first characteristic of sequential data is now data is not independent. The current data depends on past data. For example, the current word depends on past word, and the current frame in video depends on previous frame, etc. Okay, so that's the first characteristic of sequential data. And the second characteristic of sequential data is sequential data is actually variable length. Okay, because it depends on past data. You know, it depends on the how many steps of the past, the number of steps in the past. You know, you have variable length data. So sequential data is variable length. So we have two different characteristics of sequential data. The first one is data is dependent, okay, on past data, and the data is variable length. So the question is, how do we process these sequential data? So if we try to process this sequential data using neural net or CNN, then it is impossible, because in neural net we assume each data is independent. Okay, so the output of neural net only depends on input. Okay, it doesn't depend on previous data. Okay, so that's the problem. And second problem of neural net is, as you know, the input size of neural net is fixed. Okay, input dimension is fixed. So we cannot process variable length data. So because of these problems, we cannot use neural net to process sequential data. So to process sequential data, we need a new model with sequential structure, and also which can process variable length data. Okay, so RNN is one of the model. Suppose we have sequential data xi. I is the time step I, and then because this is sequential data, the xi depends on the past data x0 to xi minus 1. So that's the first characteristic of sequential data. And also because xi depends on the pass data here, xi depends on pass data here. So when you make decision on xi, you have to consider these data as well, right? So when you make decision on xi, you have to consider all this data together. So that makes this entire data variable length. That is the second characteristic of sequential data. So by using all this past data, you will make prediction of this. So that's the typical example of sequential data processing. So how do you process this sequential data in neural net? So first approach we can think of is, so this is neural net, okay? And for each sequential data, xi, you provide xi as an input, and its corresponding label value is given as output here, okay? So it's trying neural net using xi, yi, okay? That's one approach, but actually this one has some problems. In the previous slide, I explained the possibility of processing sequential data using neural net, and which is displayed here again. Actually, this doesn't work because in neural net, the output of neural net, in this case yi, depends only on xi. Okay, so this is the only input to this output of network. Okay, so when you process xi, the result of this network is actually gone. Okay, so that's the reason why this approach doesn't work. So the thing is, we need a mechanism, we need a solution to store the result of a previous step. We somehow store the result of previous step and reuse them in next step. So we need a mechanism to do that. So the basic idea of RNN is, in RNN we save the previous state of node and it is forwarded to the next step. Okay, that's the first idea of RNN. And the second idea is, as we did in CNN, the weights in RNN are shared across different time steps. So these are the two main idea of RNN, and also these are the two differences between RNN and traditional neural network. I said the main difference between RNN and neural net is twofold. The first one is, in RNN, the status of previous step is forwarded to the next step, and second one is the weights are shared, just like in CNN. So these are two differences between RNN and neural net. So in this slide, let's take a look at how these are implemented in RNN. So if you see this picture here, and this is the picture of RNN. So in this picture, if you remove this arrow here, this one, then it becomes traditional neural net. Okay, and so we have input, we have hidden node, okay, and it is normal neural net. And but in RNN we have this arrow. It means the status of previous step is forwarded to the next step as an input. Okay, that's what this arrow means. Okay, so that's the first difference in RNN. And the second difference is weight sharing. So we have two set of weights in RNN. So this is the weight between input layer and hidden layer. And this is the weight between the state, the value of previous state and current state. Okay, so that's second weight. And in RNN, these weights are same across different time steps. Okay, I'm going to explain it here in this more expanded version. This diagram is kind of this diagram is kind of expanding this picture in a different time scale. So it's more easy, I think, to read. So if you look at this, for example, this HT time step T, and this is hidden node, and this is input node. So the hidden node HT and hidden node and time T HT has two inputs. Okay, it has a traditional input, is input from a traditional input layer. Okay, XT, and in RNN we have a second input, which is the result of previous status. Okay, so we have two inputs. In traditional neural net, we don't have this. Okay, hidden node, the only input of hidden node is input from hidden layer. Okay, so that's the difference. And second difference is weight sharing. So we have in each time step we have weight. Okay, between time t minus 1 and time t. Same thing here is the weight between time t and time t plus 1. So these weights are same. Okay, and also we have another set of weights between input and hidden layer, and these weights are also same. Okay, so that's the second difference in RNN. So these are two differences between RNN and neural net. Okay, if you look at this formula, the difference is more clear now. So this one is the output of traditional hidden node. So we have input is multiplied by weight, okay, and it goes through a activation function, sigmoid or the loop, whatever, okay, and that becomes the output of hidden node. In RNN, so we do have input here, but we have another term, and we take input from previous states, okay, it's ht minus 1, and so it is multiplied by its corresponding weight, and the whole thing goes through activation function, right? So the only difference is this: in RNN we have another input which is the result of previous status. Okay, so that's RNN, and again these weights are same across all time steps. Okay, so that was the difference between RNN and neural net. So we come here. Actually, RNN has many advantages than other machine learning algorithms. The first advantage is in RNN you can produce an output and each time step. So if you look at this picture here, basically we are able to generate output from hidden layer, right? So in this picture here, let's say in each time step, okay, let's say in time t minus 1, we are able to generate an output here, whatever it is. And also here in the time step t, we can generate another output. And here, same thing, we can generate another output here. So at each time step, we are able to generate an output, I'm sorry, right? So that's the big advantage. Okay, in other machine learning algorithms, neural net or SVM, whatever, okay, they generate one output. If that is classification problem, it predicts class value. If it is regression problem, it generates one number, one line, whatever, the parameter of line, whatever. Okay. So you just simply generate one or a few numbers. Okay, that's it actually. But in RNN, because it can generate output in every time step, actually it can generate a sequence of output. Okay, not just one or a few numbers. It can generate long sequence of numbers. Okay, and if so, this is actually very big advantage. So suppose so in this particular RNN, this hidden layer generates pixel value. Okay, this is pixel value, and this one generates pixel value. Then you put all this together. Okay, this one generate pixel value, and you put all this output together. Then this whole thing becomes image. Okay. Then using this RNN, you are able to generate image. Okay. If this hidden layer generate frame, okay, frame, and the frame, then this RNN now generates videos. Okay. And if this hidden node generate word or one word, okay, and this one generate one word, then this whole thing, this whole RNN generates sentence. Okay, this can be a chatbot or a dialogue machine, okay, or a machine translator. Okay, so that's the big advantage of RNN. So that's why this RNN is actually very hot area in machine learning. Okay, so that's a big advantage of RNN. And the second advantage is RNN can naturally process variable length temporal data. So it is clear, okay, so because it depends depending on how many steps you look at in the past, okay. Let's say I'm gonna take a look like 5 steps in the past, then it's gonna be it's gonna be 5-step data. Okay, if you look at 10 steps back, it's gonna be 10-step data. So depending on the number of steps you take a look at in the past, it's quite naturally variable length data. Okay, so it is quite natural you can process variable lengths in RNN. And that was the advantages. And finally, the question is, how do you then train this RNN network? The algorithm, the training method used in RNN is called backpropagation through time. Okay, simply, this very similar to backpropagation in the traditional neural net, but it is backpropagation through time. Okay, so this one we're gonna talk about this, in a few slides. Okay, so anyway, that is the training method used in RNN, and this one you already mentioned. The weights are shared at all time steps. Okay. In CNN, it uses weight sharing. And because of weight sharing, it could significantly reduce the number of parameters in the network and improve the performance. So it's the same story in RNN as well. In RNN, it also uses weight sharing. And the only difference is in CNN, they share weight across different region, different area. And RNN, they share weight across different time steps. That's the only difference. But anyway, because in CNN, it can reduce number of parameters because of sharing, and in RNN, we can reduce number of parameters by using weight sharing as well. Okay, actually, you can significantly reduce number of weights in RNN and also in CNN. So CNN, RNN both use weight sharing. The difference is CNN, they share weights across different regions, In RNN, they share weight across different time steps. Actually, there is another weight sharing machine learning method called recursive neural net. We don't cover it here. And this algorithm share weights across different time structure. Okay, and this is widely used in natural language processing. Okay, anyway. In RNN, the other weapon, in RNN, I said the main difference between CNN and the traditional neural net is three things. Okay, the first one is weight sharing. The second one is sparse connectivity. Also, it's called local connectivity. And the third thing is the pooling layer. Okay, although pooling layer is not widely used these days anymore, but anyway, okay, that's third difference. But in RNN use weight sharing technique, but it doesn't use sparse connectivity or local connectivity. So in RNN, the connection is fully connected, okay, just like in a traditional neural net, okay, and there is no pooling layer, okay. When I talk about the advantages of RNN, I said one of the biggest advantage of RNN is it can generate a sequence of outputs, okay, not just one or a few numbers. It's just whole array of outputs. Okay, that's one of the big advantages of RNN. So in traditional machine learning method, SVM, neural net, or decision tree, whatever, and depending on whether you work on classification or regression, it generate just one or a few numbers. Basically, that's it. Okay. But in RNN, because it can generate output in each time step. Okay. So RNN can generate many output in sequence. Okay. So you can basically generate sequence of output. Okay. So that's one of the advantages of RNN. So I explained in previous slide. Okay. So actually, this is called sequence to sequence learning. So sequence to sequence learning is RNN RNA is to process sequence data. The basic assumption of RNN is RNA is meant to process sequence data, right? So and also I said the advantage of RNN is to produce sequence of output, right? So input is sequence data, output is sequence data. That's very interesting, right? So that's why we call it sequence to sequence learning. So that's one of the advantage and one of the biggest characteristic advantage of RNN method. So since RNN can produce an output at each time step, it enables what is called sequence to sequence learning. So the definition of sequence to sequence learning is to give an input. Input is sequence learning by assumption. Okay, by assumption of RNN. RNN is meant to process sequence data. So given sequential input, algorithm generates a sequence of output. So that's the definition of sequence to sequence learning. Input is sequence, output is sequence. So this one shows some example of sequence to sequence learning. So in this case, this is actually not sequence to sequence learning. Input is a single data, output is single data. It's one-to-one. So just traditional classification problem. Okay, so you don't have to worry about this. Is not actually sequence to sequence learning. One data, one input, one output. Okay. In this case, these represent different time steps. Okay, so you provide one data here. So in this case, input is not sequence. Input is just one data. Okay, and then in each time step, it generates output. So it is called one to many. Input is one, output is many. It's called one to many. So example of this application is image captioning. So you provide a image, okay? So So image, the one data, image. And this RNN actually produce many outputs, and each time that it produces output, this whole thing becomes sequence of output. Okay, so this, if this is each output is word, let's say this each output is word, okay, language word, then this whole thing is sentence, right? So input is image, right? And this one is a sentence, okay? So a typical application of this is you give a picture, okay? So you give a picture, let's say you give a picture of a person standing in front of a house, whatever, okay? So you give a picture of a person standing in front of a house, okay? So you just give a picture, nothing else. And this RNN algorithm read the picture and generate sentence saying a man standing in front of house. Okay, think like that. A man standing in front of house. Okay, something like that. So that's a typical example of sequence to sequence learning in this case. This is another example of sequence to sequence learning. In this case, input is sequence and output is just one. Okay, so you give the typical example of this is you provide a sentence. So sentence consists of many words. So each one here is a word. Okay, English word, whatever. Okay, you provide the words at the end. So in this step, we do not generate words. Okay. You do computing here, but you do not generate output here. So at the end, you generate one output here. So input is sequence, but output is not sequence. Output is just one output. So it's called many to one. So typical application example of this one here is sentiment analysis. The sentiment analysis is, so this one is like document, okay, text or document. So you give a sentence or document. So this RNN method read the document word by word, and at the end, it gives a sentiment of document. Like this sentence, this document is, in the mood of happiness or in the mood of sadness or angry, whatever, okay? It simply classifies the document, the mood of document, okay? You can do that. So that's sentiment analysis, okay? So it's called many to one. Another example, this is very popular actually, okay? So another example is many to many. So in this case, these both are many to many, but it's a little different. So in this case of many to many, so you have a sequence of data. You provide input. So input is sequence. Okay. So when this algorithm read input, it does not generate output. It just read input. Okay, and doesn't generate output. But when input is done, then it starts generating output. Okay. So this RNN algorithm method, when it read input, okay, it doesn't generate output, okay? It waits until input is done. When input is done, it starts generating output, okay? That's the first scenario example of many to many. So this one is very popular, and the typical example of this application is machine translation. Let's say you give, English sentence here, okay? And this RNN algorithm just wait until it finished reading the input sentence, okay? And then when input is done, it starts generate, let's say, Korean language, whatever, okay? So it's machine translation. So it read entire input, and then when input is done, it starts generate something, okay? So a typical example of this is machine translation. Or another example is chatbot. So you as a user, you input sentence, whatever, okay? You talk you give a sentence to RNN machine, RNN method, in this case chatbot. So chatbot read your sentence, and then when your input is done, it starts generating sentence. So each of these is word, 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 word. So this example of chatbot. So this is example of another example of using a many-to-many case in sequence-to-sequence learning. This one here is another many-to-many. Input is sequence, output is sequence. So in this case, this one here, RNN, just wait until input is done, right? But here, in every input, it generates output. Okay, so let's say the example of this is, let's say you give a frame of video. For each frame, it classify the frame, whether it frame is whatever. Okay, so that's another example of many-to-many. Okay, so this is called sequence-to-sequence learning. Again, as I said, one of the big advantage of using RNN is it can generate sequence of output, not just one or a few number output. It can generate big, long sequence of output. Okay, so if this output, let's say this output is pixel value, the whole thing becomes pictures. You have seen the example of the deep learning algorithm generate images. Okay, that's the case where we use RNN, okay, to image data, and sometimes you see deep learning algorithm generate music, composing music. So in that case, it's the output here is just sound, small sound. Okay, so altogether it becomes music. Or you can do many things. It can be picture, word. If each output here is word, then the whole sequence becomes sentence or document. It can generate document or a sentence. Okay, so it's a lot of potential application. Okay, that's why this RNN is very popular these days. Now take a look at one example of sequence-to-sequence learning. So in this example, we're gonna train this RNN to generate HELLO in this order. That's the goal of this training. So actually, this type of work is called language model. So language model is, in general, is in a sentence, you're gonna predict next word using a previous word. Okay, so in a sentence, there are many words. Okay, so when you generate a sentence using the previous word you already generated, you wanna predict next word. That's a language model. Okay. Usually this language model is based on word level. That means we predict next word, not character. But in this case, to make things simple, we use character level. That means we predict character instead of word, because in word we have so many words. Character we have only 26 character. So anyway, the vocabulary we have is only 4, HELO. Okay, instead of 26 vocabulary, we have 4 letters. So again, the goal of this learning is to make this RNN to generate letters HELLO in this sequence. That is the goal of this learning. So let's say we have RNN. In this case, we have 3 hidden nodes. And the way we train this RNN is the following. So in the first time step, we provide input H. Okay, so input H is given. By the way, if you look at this input node, this says 1000, right? So this form is called one hot encoding. So in this case, we have only 4 vocabulary. So in each bit here represents one letter here. So this represents H, E, L, O. So this one is 1. The rest is 0. That means this form is, this represents H. Okay. So in the same way, this one, the second bit is 1. That means this E. So this represents E, and this one represents L. Okay, so we use one hot encoding to represent letter here in this example. So anyway, in the first step, we give H as an input. So the goal of learning is, again, we're gonna make this RNN to generate ELLO. We give H as a kind of seed character, then this RNN must generate the rest ELLO. So altogether becomes HELLO. So when you give H, this RNN should generate E as an output. Okay. So input is given, the H is given, and using this formula, so I explained this in a previous slide. Okay, so the value of hidden node is computed using input and the previous state, right? So this is the result of hidden node using input and the previous status. In this case, there is no previous state, right? This is the first step. So in this case, in the beginning, the weights are given randomly. Okay, this weight initialization. You initialize weight, so we're going to use that one, initial weight here. So anyway, using this input and previous weights, previous values, in this case initial weights, you compute value of hidden layers. So out of these hidden layers, you can compute output values. Okay, you can compute output values. So if this output is E, okay, if this output is E, then the answer is correct. The output is correct, right? Because I said, when I say H, this RNN should generate ELLO. Okay, so if this output is E, it is correct. But this output is not correct, there is error, right? So depending on the output of this hidden layer, we compute error. Okay, we use error function, whatever the error function is, we use error function to compute this error between the output and the true values. In this case, true value should be E, because our goal is HELLO. Okay, so we gave H, output should be E. Okay, so depending on the output of this hidden layer, we compute error in this step. Move on. Next step, we give E as an input. Okay, then in this hidden layer, the value of hidden nodes are computed again as this. So it has 2 input, this one, and it also uses the value of previous state, right? So using these 2, it computes its hidden values, hidden node values, right? So again, using these hidden node values, it generate compute output here, okay? And then in this case, the output should be what? Output should be L, okay? HELLO. So we gave input, so next letter should be L, HELLO, okay? So output should be L. So if this error was L, there is no error, but if this output was not L, there is error. So anyway, we define error here using whatever function you like, okay? Error function you like. So keep going. So for each time step, okay, you give input. Also, you give input, and this based on these hidden values, you generate output. Using those output, you compute error. Okay, and here same thing. You give input, and using this one based you generate output, and using this output you generate error. Okay, so in each step we have error, 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 error. Okay, sometimes the error is zero. Okay, but some other times the error is not zero. Anyway, so in each step we have error, and we add them together. Okay, and that is total error. And the goal of learning is we're going to minimize the total error. That is the goal of learning in this RNN case. This slide is very similar to the previous slide with a little more explanation. So again, the goal of learning is make this RNN to generate hello, H-E-L-L-O. And so when we give H, it should generate E-L-L-O. But we have to train them first, okay? So to train them, we provide training error like this H-E-L-L. Okay, so for each letter, let's say H, this RNN should generate E. And the next step, we provide E as an input, then RNN should generate L. And next step, we provide L, and RNN should generate L. And final step, when we provide L, it should generate O. Okay, so these are the training error. So for each training letter here, this RNN should generate correct answer E-L-L-O. Okay, that's the goal of learning. So in the first step, we give H. Again, this is one hot encoding of H. And using this, and in previous state there is no previous, we use initial weight. So using this initial weight and this input, one hot encoding, we compute hidden layer values. So using hidden layer values, we compute output node values. So in this case, we have in this output layer, we have 4 nodes. The reason is we have 4 vocabulary, okay? Our prediction is you choose one of these 4 letters. So that's why we have 4 nodes. So each node here represents each letter here, H, E, L, O, okay? So anyway, using this hidden layer, okay, we compute the value of output layer here, okay? So in this case, we choose the maximum likelihood. So in this case, 4.1 is highest one. So the prediction, the output, okay, output of in this time step is actually O, okay, because this is highest likelihood, 4.1, which corresponds to O. So in this case, output of RNN is actually O. But the true value should be E, right? So we have error. So using, let's say, I think maybe you can use cross entropy. Okay, so you can use cross entropy to compute the error between this output layer and the word-hot encoding of character E. So this is what happened is you want to compute error function using cross entropy in this case. Then what you have to do is you represent E like this using one-hot encoding 0, 1, 0, 0. Okay, so we have 0, 1, 0, 0 here, and we have another distribution, this. So we have 2 probability distribution. Okay, 0, 1, 0, 0, the true value. Another distribution, this one. Okay. So using cross entropy, we are able to compute error in this case. Okay, you can use some other error function, but okay, but in this case, let's assume we use cross entropy. Then that's the way we compute error in this case. So anyway, we compute error. In this case, this is error. This output, in this case, output is O. Okay, true value is E. So there is error. So you compute the size of error using maybe cross entropy. So we have error here. Okay. The similar way, in next step, move on, and we give now E. Okay, because our goal is to generate HELLO. So we provide data in this sequence HELL. Then in each time, this output should be ELLO. Okay, that's how we trained RNN. So we next step we provide E, okay, and in hidden layer using this E and this using previous state, you compute the hidden layers. Using a hidden layer, you compute now output layer, okay. So you choose maximum as output. In this case, maximum is this again. So output is O. So again, it says error. The correct output should be L, but the output of this RNN is O. We choose maximum likelihood. So this is error. So again, you compute error, size of error using maybe cross entropy. Okay. So we have error here. We have error here. And move on. In next step, same thing. You provide L. So using L and this previous values, you compute the hidden layer. Out of hidden layer, you compute output layers. So you choose maximum. In this case, this is maximum. So it's L, right? So output is L. Correct value should be L. So in this case, correct, right? So there's no error actually in this case. So move on. So final output is L, input is L. So you compute again hidden layer values. Using hidden layer, you compute the output layer. So you choose maximum. This is maximum. So maximum is O. This one is O, right? So you output is O, and true value should be O. So this is no error. But this is correct. This is correct. Okay. Actually, there is no error in these two cases. These two are errors. So the way we train this RNN is like this. In each time step, we compute error, okay? And the total error is used to summation of all these errors, okay? So that becomes, this total error becomes the error function, okay? Loss function, that becomes loss function, error function. And we use backpropagation for this entire network. We use backpropagation to update all these weights, okay? And the error function we use is this, the summation of error in each time step. So that's basic idea of training this RNN. So we use backpropagation, but a little difference here is we use backpropagation using different time step, right? So a little modified version of backpropagation. So we call that propagation as backpropagation through time. So we're going to explain this next slide. But basically this is backpropagation, but in RNN case, we use backpropagation in different time step. Okay, so we call it backpropagation through time. Okay. So anyway, the goal error function is you add all this error together in each type step. Okay, and that becomes the final loss function, error function of backpropagation. A second thing you have to remember is, so you use backpropagation, but these weights, this blue arrow, these weights, and these green arrows, these weights, and these red arrows, red weights, should be same. Okay, and these four are again same, and these three are again same. Okay, so this is backpropagation, but a little modified version of backpropagation. So there are two modifications here actually. The first modification is, this is backpropagation, but this is backpropagation in different times, using different time steps. And second modification is if these arrows, this weight should be same. These are same, these are same, these are same. Okay, that's how we train RNN. Okay, now suppose the training is done. So we gave H, E, L as input and make the RNN to make the RNN generate E, L, L, O as an output. We use backpropagation. We define the error function for each time step and add them together as a total error function. We use backpropagation through time to minimize the error. Okay, so training is done. Okay, now it is time to actually generate this letter H, hello, H-E-L-L-O. So let's do it. So you give H as a seed character, then this RNN must generate E-L-L-O. Okay, so you give H, this is input, and this is hidden layer. So in this case, the value of hidden layer actually, the previous case, in this case here, is the hidden layer values after training is done. Okay, so in the beginning we give H as an input, right? And when you can compute this hidden layer values for the previous value here, in the previous slide in training we used initial weight here, right? Because that was the first time step. But in this test time here, in the previous value here, this one is the result of hidden layer after training is done. Okay, the final hidden layer values after training is done. Okay, so training is done. Okay, then at the end we have the hidden layer values, right? That value is used here. Here, it comes here. Okay, so that is used as an input in this stage. Okay, so using those values, okay, as the previous value, and using this input, you compute hidden layer values. Out of this, you compute output layers, and we have another layer called softmax. I wonder whether you remember this softmax. I explained this in gradient optimization method chapter. So the goal of softmax is you change this score into probability distribution. Okay, so that's the goal of softmax. Why do we change this score, output score, into probability distribution? The reason is when you choose output, okay, when you choose output in this time step, we do probabilistic sampling. Okay, we do not simply choose the maximum score value. We don't. Okay, what actually do is we change it to into probabilities, and actually this probability represents the probability of being selected as an output. Okay, so in this case, the H here, the probability of H is 3, probability of E is 13, probability of L is 0, probability of O is 84. Okay, so you do sampling, probability sampling out of these 4, and it looks like a probably, and you know, this one is highest probability O. I think this probability of this O has the highest probability, so probably this letter O should be selected. But in this case, we assumed, well, for some reason, letter E is selected. Okay, it's E, is probably 13 is selected. Okay, sometimes it can happen. Okay, so we assume that this E is selected. Okay, and it comes in here as the next input here. So repeat, we use this value, hidden values, and use E as an input. The output of this one, output of previous state comes in as input here. So using these two, you compute a hidden layer, and using this hidden layer, you compute output layer and change it to probability distribution. And again, you do probability sampling. In this case, let's say L is selected, okay? So not a weird example, 0.5, okay? Anyway, this is example, okay? So this L is selected, and then L comes in here as an input in next step. So L input using previous state, you compute hidden layer and output layer. Now it changed to a probability distribution using softmax. You choose one here. Now this time it is L is chosen. This time it should be correct, okay? 68%, the highest value is L, 68%, which is L. So L is chosen, and L now comes in input. In next step, same thing, compute hidden layer, compute output layer, and the probabilities are given like this. So you choose, now you choose O, this one, okay? Looks like okay. So this is chosen, O is chosen, okay? So input was H, and then the RNN have chosen E, L, L, O, okay? So that's how these RNN generate data, okay? After training is done, when you give initial seed character, now the RNN automatically generates this sequence of data. E, L, L, O. So altogether H, E, L, L, O. This example is a little weird because in this case we do probabilistic sampling. So these are kind of probabilities of being selected. I told you, okay. So in this case, I think in practice, probably this should be selected, right? It's the highest probability. But this is just for the sake of example, and for some reason E was selected. Its probability is just 13, okay? Anyway, probability 13 beats probability 84. So we assumed that, okay, that way, and this E is given as input. In this case, again, we assumed L is selected, probability 5 is selected over probability 50, okay, for some reason. So that's how it works. So you may wonder, okay, so why do we select, you may simply choose the best probability here, okay? So maybe the choosing the best probability is more reasonable choice, right? Instead of using this probability sampling, you may wonder, well, why not choose the best, highest score, okay? The reason is, it's probabilistic sampling is better, okay? And so you give more diversity, okay? So in this case, if you use probabilistic sampling, you give more diversity. So, and right now, this probability, this one has the highest probability. And the thing is, actually there is no guarantee that this is correct. Okay, there's no guarantee that this probability is correct. Okay, so we need to give more diversity. Okay, there is no 100% accuracy that this is correct. Okay, so that's why we choose probabilistic sampling. Actually, that is much better than rather than choosing the maximum value. Okay. That's the reason. And also you may wonder, okay, in this case, we assume that it choose E instead of O, okay? So what if this RNN choose O here, okay? You gave H and this one have chosen O, okay? Then we messed up, right? We give H, it's supposed to generate H, E, L, L, also H, E, L, L, O. That should be a correct output. But what if we gave H and this guy RNN generate? Oh, yeah, we messed up, okay? Then what happened? Then the reason is the training is not complete, okay? There is something wrong in your training, okay? Maybe you need more data, or your network, you need to modify your network. Maybe you need another layer, or increase hidden layer, or reduce hidden layer, or you change the activation functions, optimization method, whatever, okay? So it's a little tricky, but training is not perfect, okay? That's the problem you have to work on, okay? So that was the test time process. So you give initial input, the RNN should generate these output in sequence, okay? So that's the example of sequence learning. Now let's talk about backpropagation through time. Backpropagation through time is very similar to ordinary backpropagation. The only difference here is we compute error in each time step here and add them together, and that becomes the final error function of backpropagation. And we're gonna minimize that total error. We're gonna minimize this total error using backpropagation using this entire network, okay? So backpropagation tries to minimize total error for this entire network. That's backpropagation through time. So the next question is then, these are time steps. So how many time steps you're gonna consider? Okay, you wanna take a look 6 previous step, or 10 previous step, or 100 previous step, etc. Okay, so you have to decide. But the thing is, actually you decide. Let's say I'm going to take a look at 6 previous step only. I don't care about the rest here. I don't care about the 7 or more steps back. Okay, I don't care. I only consider 6 previous step only. Okay, that's what actually happens. So that's why we call it truncated. Okay. We don't consider all the histories, okay? We just consider 6 or 7, whatever, previous steps. So that's why sometimes it's called truncated backpropagation through time. So anyway, the problem, this backpropagation through time has problem, and the problem is, again, vanishing gradient. Okay, welcome to vanishing gradient again. The problem is, so if you increase this step size, let's take a look at 10 previous steps or 100 previous steps, then what happened is, if you use backpropagation through time, what happened is, there are some changes here, around the current time step, that if you go back 10 time steps here, actually there's nothing happens here, okay? There are quite change here near the current step. Well, gradually it becomes smaller, and basically nothing happens way back here. So it's the same thing happens in neural net. If in neural net if you have many hidden layers, near the top layer, near the upper layer, there's quite some changes, right? But if you go down go down deep and near the lower level layer, actually there is nothing happens, virtually nothing happens, okay? And that is called vanishing gradient. So even though you add many hidden layers, nothing happens near the bottom, because it doesn't make sense. Adding many hidden layers in neural net, it doesn't make sense because nothing happens the bottom layer. That's why we come up with a new method called deep learning. Okay, so change the training method. That's the basic idea of deep learning. So same thing here in backpropagation through time. So if you consider many previous time steps, exactly same thing happens. Yes, there are quite some changes here, okay, but gradually back here, like 10 steps or more in previous step, virtually nothing happens, okay. So that's the problem. So again, we have vanishing gradient problem again in RNN, okay. So that's problem. So if you simply use RNN, okay, to take care of sequential data, what happened is, well, if you look, you can look back like 2 or 3 steps back, that's fine. But if you consider like more than 5 steps or some more, then it doesn't make sense because more than, let's say, 3-4 steps back, there's nothing happens, okay? So that's problem. Just like we have the vanishing gradient problem in neural net. It's exactly same problem, okay? So we need to do something to solve this problem, right? So that is why we come up with a new method called LSTM and GRU, which will be explained later. This slide explains why the vanishing gradient problem happens in backpropagation through time algorithm. So let's say we have RNN. So these are time steps, 0 time step 0, 1, 2, blah, blah, x time step n, right? These are output, these are input, okay? So I said in RNN, we define error in each time step. So let's say this is the error of each time step. So let's k is the time step, k equals 0, 1, 2, n, right? This is k. So for each time step, let's say L, yk hat is error in time step k. Okay, this is error in time step k. And the total error Jn is the summation of all errors in each time step, right? So this is total error. So in backpropagation through time, we are looking for the W, the weight in the RNN network. We are looking for W weight, okay, which minimize this. Okay, so and we use gradient descent, and gradient descent means we update weight by using this formula, right? So again, it's in backpropagation through time. We define error in each time step. This is error in each time step. This is true value. This is predicted value. This is loss function between these, using these two, right? So this is error in each time step. It is error in time step k. So total error is summation of all this error. And we use gradient descent. That means each weight in RNN network is updated like this, using this formula. So yeah, good. Then the thing is, let's take a look at this one. Okay, you take derivative of Jn in terms of W. So let's take, when you compute, you're going to compute this one, right? This one continues from previous slide, and backpropagation through time uses gradient descent. So as you can see in previous slide, you update your weight using this term, right? So if you take a close look at this term, because of the chain rule, it consists of these things, okay, these things. So you want to take derivative of Jn with respect to W, then you have to take derivative of Jn with respect to output first. And to take derivative of Y output, you have to take derivative of Yn with respect to S hidden layer n. I'm sorry, the time step n Okay, so keep going. So for each, so here, take a look at this one. Here, this one is for every time step, you have to compute this. Okay. So the thing is, you gotta compute this one, and then this one actually consists of this thing, and for each time step, you compute this. So if you have many time step, then again, for each time step, you have this. So you have many time steps, and then what happens is these values, many cases, these values are small, especially when you use sigmoid or hypotangent. These values are usually very small number, and you keep adding it. Okay, so these are small number. You keep adding it, and so this whole thing is almost zero. So this whole thing almost zero means this is zero. That means in gradient descent, nothing happens. There is no update in the weight values. So that's the vanishing gradient problem. So actually what happened is, if you have many time steps, you look back many previous steps. What happened is, maybe there is some change in 2 or 3 previous steps, but like more than 5 previous steps, there's nothing happened actually. Okay. And what happened is, it doesn't remember what has happened in the past, like more than 5 steps or something like that. Okay, it doesn't remember it. So since things happened like back here, doesn't make any difference in the current time step. Okay, so that's what happens. And if you simply use RNN, then you're gonna see vanishing gradient problem, and way back here, data what happened in way back here actually doesn't make any difference in current time step. Okay, you can also say this current time step actually forgets what happened back here. Okay, that's vanishing gradient problem in RNN. So I explained the vanishing gradient problem in RNN. So if you simply use RNN in sequential data, you're going to see a vanishing gradient problem. So for example here, so let's say you want to predict whether you want to use chase or chases. So in this case, chase is correct because of my dog, right? So in this case, that's fine. If you use RNN here at this point, you can remember, you can take a look at this my dog, just one step back. Okay, so that's fine. But if you use RNN for this sentence, so you have to decide whether chase or chases. Then you have to go back here. So 1, 2, 3, 4, 5, 6 steps back. So probably you're gonna have vanishing gradient problem here if you use RNN. So that means way back here, actually data here, it doesn't have any impact on this time step. So this one, just simply forget this. Okay. So because simply it cannot remember this one, it has no idea which one is better. So that's the problem. That is vanishing gradient in this case. So the question is then how to solve this vanishing gradient problem. So a couple of options here. The first one is, if you initialize the weight values in a proper way, sometimes it reduces the effect of vanishing gradient. But it is a little limited. Okay, so instead of that, the second option is we use ReLU activation function instead of sigmoid or hypotangent. This option is already used in neural net. It's quite effective actually. Okay, because in hypotangent or sigmoid, the value is close to 0 or 1. Its derivative is very close to 0, right? So because of that, we have a vanishing gradient problem. With the ReLU, the derivative is either 0 or 1. Okay, very clear. Okay, 0 or 1, very simple. So it doesn't have a vanishing gradient problem. But problem of the ReLU is, as I as I said in the gradient optimization method chapter, the problem of Lulu is many of neurons using Lulu is actually dead because the output is zero. Okay, so Lulu has its own problems. Okay. So we have third answer, okay, third solution, which is the most popular one. Okay, so instead of vanilla RNN, the ordinary RNN, we use what is called LSTM or GRU. LSTM stands for, means long short-term memory, and GRU means gated recurrent unit. So instead of vanilla RNN, we use LSTM or GRU. So I'm going to explain these two a little later. I explained the vanishing gradient problem in RNN, and to solve the problem of vanishing gradient, actually we use LSTM or GRU instead of RNN. So here we go over LSTM first, and a little later we're going to study GRU. So this is the picture of LSTM. Okay, and the first difference between LSTM and RNN is LSTM contains memory cell. Okay, that's the first difference. So the question here is, so in LSTM we actually have two status value. Just like in RNN, we have a status value of a hidden node, and we have a status value of a memory cell. So the question is, in current state, how do you compute the next state value of memory and next state value of hidden node? Okay, that's basically the mechanism of LSTM. So I'm going to explain this procedure kind of in a higher level, abstract level first, and then in next slide I'm going to give more detailed explanation of how these are implemented. Okay, so the first thing we do is in RNN, when you compute the output of a hidden node, the next state value of hidden node, what did you do? We used current input and the previous value of a hidden node, right? By using this, we compute the value of next state, right? So we do exactly same. By using these two, okay, this ht-1 and the current input, we compute the output of hidden node in next step. This is exactly same as in RNN. Okay, so this is the output of hidden node. And then in LSTM, I said there is memory cell, so we have a memory value here. So we have a memory value here. So we have two values. The output of hidden node, okay, you compute this using these two, just like we did in RNN. And LSTM has memory values, so we have memory value here. So we simply add these two values together. We do addition between these two, okay? And then the result of addition is moved to, so addition of this result becomes the next value of memory cell. And also this result of addition becomes the value of next hidden state, next hidden node. That's the higher level description of LSTM. Okay. But actually in LSTM, we have some other differences, some other actually catches here. LSTM has three gates. It's called forget gate, input gate, and output gates. Actually, these gates actually controls the flow of information in each step here. So I'm gonna explain that here. So I said we compute the output of hidden node here, okay, and then you use the memory cell value here and add them together, and the result is given to next memory cell and also given to next hidden node values, right? But in each step here, so for example, in this step, when you use memory value, there is a forget gate. So what this forget gate does is, this is actually gate. So this is very similar to gate. When you enter a building, there is a security person, okay, so they decide whether they gonna let you in or not. Okay, that's exactly same as gate. So this one is gate, and it actually determines how much information of this memory cell pass through this here. Okay, so if the forget gate is 0, actually no information pass through here. Okay, this becomes 0, even though regardless of the value of memory cell, this value is 0. Memory value used here is 0. And forget gate is 1, so this information is given in its entirety. Okay, there is no loss here. And there is another gate called input gate. So you compute the output of hidden node in next state, right? And you use it here, okay? But when you use it, there is an input gate. You have to go through input gate. So exactly same. It is input gate determines how much of the output here goes through here. Okay, so if an input gate is 0, this is 0. Okay. Okay, regardless of the output of this hidden node, this output becomes 0. And if input gate is 1, this whole information passes through here. Okay, that's input gate. Finally, so the output of this addition moved to the next value of memory, and also this output moved to the value of next state hidden node. But when he moves to the next state hidden node, there is output gate. Also, this determines how much of this information moved to HT. Okay, the same thing. If the output gate is 0, this becomes 0. Okay. Now output gate is 1. This information in its entirety is passed through here. Okay, so that's the 3 gates, which actually determines how much information goes through in each pass here. So in next slide, I'm going to give more detailed explanation of these gates. So in LSTM, as I said, we first compute the output of hidden node using this formula here. So we apply hypertangent using both HT-1 and XT. Again, this is exactly the same formula used in RNN. So using these two, we apply a hypertangent, and this information path through here, okay? But when it does, we have this one has to go through a gate called input gate. Okay, that's what I said. So we compute output of hidden node first, but it goes through input gate, and the value of input gate is between 0 and 1. So depending on the value of this input gate, maybe this entire information is passed through here, or no information is passed through, or half of them pass through, whatever. Okay. So how do you implement this input gate? Actually, we have 3 gates: forget gate, input gate, output gate. All these 3 gates are implemented in exactly same formula, which is described here. So only 3 gates use exactly same input, HT-1, XT, and then they apply sigmoid. The reason they apply sigmoid is sigmoid returns, it ranges between 0 and 1. Okay, so this function, this gate returns value between 0 and 1. Okay, so that's why we apply sigmoid as an activation function of this gate. So using this, you compute the forget gate, okay, and then using this forget gate, you determine how much of this memory value is used in this pass, and also you compute using these two. You compute the input gate using a sigmoid function, okay, and also this determines how much of this output of hidden node is used here. Okay, and then so this information goes through forget gate. This output goes through input gate. Okay, so the final result here are added together. So the result is passed to the memory cell in next step, and also this result is passed to the hidden node value in next step. But when this is passed to the hidden node, it must go through another gate called output gate. Again, this is same thing. It reads these two and applies sigmoid, and it ranges between 0 and 1. Okay, so depending on the value of output gate, it may I don't know, kill entire value of output here, or maybe full information is given to the HT, or maybe half of them go through here. Okay, depending on the value of output gate. So that's how these the gates, 3 gates work in LSTM. So this one here shows the implementation of each gate. So these are inner product between these weight, and these are input. Okay, so basically this gate, forget gate, input gate, output gate, are small perceptron network, very tiny perceptron network, and the activation here is sigmoid function. So it's very small perceptron network with activation with the sigmoid activation function. That's these 3 gates. Okay, and this one C tilde T is the output of hidden node. For this one we already learned it in RNN. This is exactly the same formula used in RNN to compute the output of hidden node in next step. So we know this, I assume. So finally, when you compute this output here, we simply add these together. Okay, we add this value and this value. Again, this value went through forget gate. This value went through input gate. Okay, so using these two values, we do addition here. That's what I made here. Okay, you simply add these together. Again, this one went through forget gate. This output went through input gate. Okay, so you simply add these two. Okay, so this one is moved to the next memory value, and also this is moved to the value of hidden node in next step. But when it moves to hidden node, it must go through output gate. Okay, so this one output is this output result of addition go through output gate. That's final value of hidden node in next step. Okay. So the advantage of LSTM is the first, the vanishing gradient problem is solved by using LSTM. It has a memory cell, so it actually stores some information from the past data. So that way it can solve vanishing gradient problem. It can remember now the past data. And it has a lot of parameters. It has parameter in gates and in many other area. It has many parameters. But back propagation through time actually tunes automatically, so you don't have to worry about all the parameters of weight in LSTM. So no parameter tuning is necessary. Because of this LSTM, it has memory. You don't have to worry about your long-time dependencies. It is able to now remember, all the data like 10 steps ago or something like that. Okay, so LSTM solves the vanishing gradient problem, and it also solves the long memory limitation problem. So sometimes LSTM can learn sequences with more than 1,000 steps back. So that's quite a big advantage of LSTM. So we studied LSTM, and actually there is another gate called GRU, gated recurrent unit. This GRU is simplified version of LSTM. This model is much simpler than LSTM. It has only two gates, and it has less parameters, and it's much faster than LSTM. But even though this model is much simpler, its performance is quite competitive with LSTM. So many people use this GRU these days. Okay, this is simple, but it's quite competitive. So let's talk about this GRU here. This picture shows the diagram of GRU. So as I said, we have two gates here, reset gate and update gate. So let me explain this part first. So in RNN, when you compute the output of hidden node, we use input and the previous value, right? So this is what happens here, but the only difference here is there is reset gate in between these two. So if reset gate is 1, okay, reset gate is 1, this is exactly same as the way we compute hidden node output in RNN. Okay, so if this is 1, actually this becomes this exactly same as the way you compute hidden node output in RNN. Okay, but if this reset gate is 0, okay, then this value is gone, previous value is gone, and you simply use input data only and compute this. Okay, so anyway, depending on this reset gate value, you compute the next hidden node value. So let's say it's h hat. So this I'm going to call this candidate of next hidden node value. Okay, so this is candidate of next hidden node value, and then we have this update gate. So what this update gate does is, so we're gonna decide, the final. We're gonna decide the final output of hidden node in next step HT. We have two options, two choices. Previous value of hidden node, and this one we just computed just now, and it's another candidate of HT value. Okay, so which one you're gonna choose? Okay, which one you're gonna choose? You're gonna depending on the value of this offset gate Z. Okay, if this value is 0, okay, 0, then this is 0. Okay, you ignore the previous value, and 0 means you use this one. This value becomes the value of next hidden node. Okay, and this is 1, then this is 1, this is 0, and this is ignored, and this is 1 means don't worry about this, and the previous value, regardless of this, forget about this, and the previous value simply becomes the value in next step. Okay, and or maybe if this update gate is half 0.5, maybe we take half of this and half of this and combine them, addition, and that result becomes the value of next hidden node. So that's the basic idea of GRU. This slide shows the implementation of GRU. So as I said, a GRU has two gates, reset gate and update gates. In LSTM, it had three gates: forget gate, input gate, and output gates. And those gates were implemented using xt and ht-1 as input, and they use sigmoid as an activation function. So same thing here in GRU, it has two gates, and these gates also use xt and ht-1 as input, and they use sigmoid as an activation function. So if you look at here, is it reset gate? It use xt input and ht-1, the previous value of hidden node, okay, and then they apply a sigmoid activation function. This is reset gate, and this is update gate. Exactly same. They use xt, ht-1, and sigmoid function here, and it's exactly same. Actually, this implementation is exactly same as those gates in LSTM. So these LSTM gates, forget gate, input gate, out gate, are also implemented like this. So all the gates are implemented exactly same here. Okay. So anyway, by using these two values, in this the case of ht-1, it goes through a reset gate. So using this xt value and this h value, which went through reset gate, using this you compute new candidate value of ht. We call it h prime t. Okay, finally, depending on the update gate, we decide, so as a final value of ht, the new value of a hidden node in next step, we have to decide which way do we go. We have two options. Okay, the previous value of hidden node ht-1, okay, that's first option. And second option is the new value, okay, the new candidate of the value. By using these two values, we have a new candidate of ht. So which way do we go? So it depending on the value of z, if g is, look right here, if g is 0, okay, we go with ht-1 only. We use this one only. If g is 1, then forget about this, and we simply use this new candidate here, the result of this computation. Okay, so if this z is half, maybe we choose half of this and half of this. Okay, so that's how we implement the GRU gate.